And this is where we see a variety of different movements here, of different dances. And the one thing you'll notice are different times of day. They're in different locations. And what that means is they probably trained it up with one set of dance routines, downloaded it, tested it, went over, did another one. So that means they are able to get these moves. Or, they may be getting some rigging from, Blender or some others to get some idea what these dance moves are, and then put them in there and then get it to learn how to do it. With this actuation strategy, and then download it and go. So you see, it's really pretty impressive. And the takeaways here first is that it's full body control. There's no doubt about it. This is the Gen 2 bot. Let's be clear on that. It's not the Gen 3. But right here, some of these steps, they're pretty quick. And I just wish they'd send out one more video, and that is Optimus walking now with RL. I'm assuming it can walk 3 miles per hour now. So please, Tesla, if you're out there listening, that's all I want. A really prosaic update of it just walking normal speed. I don't care about running. And that will tell me that, oh, okay, you're ready. Because it's very clear it can change direction really quickly. That's always been the problem with many applications, is that they pick up the box and then they have to turn around to walk in another direction. And that's where all the cycle time is lost. But I need to see the update.
There's an explosion of humanoid robot vendors around the world, all making their own versions. It's still too early to tell which design will be a winner and which might be a dead end. Tesla, it seems, is not only taking a very different approach for their designs for their hands, but also their choice for how the hips, legs, and feet work. It's much different than other companies. Tesla's Optimus might not be able to play soccer, but perhaps it was designed like this on purpose for other reasons. Today, we have a robotics expert, Scott Walter, a two-time robotics company founder, joining us to explain how 17 robots were designed and why. Welcome back, Scott. Appreciate you very much.
Yeah, welcome back, Herbert, because I'm taking over the show today.
You are. This is going to be a very deep dive. We're going to learn a lot. You took, I love this research you did. Obviously, you got the experience, but you're going to teach us a lot about robots. There are 17 vendors. Each of them chose a slightly different design. There's there's a design that everybody likes, but for some reason Tesla is out of the pack. How does this impact, the hips, the legs, the feet? How does that impact the kind of useful work that they may or may not be able to do? This is really important. Thank you so much, Scott. Let's take us through this.
Yeah, so I think the short answer to that is it's kind of nuanced, and I want everyone to be patient. We're going to be going on a long journey here to explain that, because there is no perfect design out there. They all have trade-offs. And so there may be some trade-offs that Tesla has made, but there's all trade-offs others have made. And that's what we want to do, is we want to kind of explore that design space and see what's going on, because remember, they're not exact copies of humans. So there's things that they will be able to do that we can't, and there will be things they can't do that we can. And so I need to set the stage for that. And I hope everyone is a little bit patient, because it's going to be worth the ride. So the first thing I'm going to do is I'm going to start sharing a little bit here of some of the thoughts that I've put together over the last couple of months. And the first thing is, of course, we're going to talk about this, which everyone has been a buzz about. And to really understand what's going on here, I just can't give you a hot take. We need to make sure we get that nuanced background going on in here that will make everything worthwhile. So stick around. We're going to go into this pretty heavy. And when we get to it, you're going to understand the payoff. Yeah. So the next thing is, whoops, just a second here. I might want to redo this a little bit here. Okay. So if we remember, back in December was the last meaningful update that we had from the Tesla bot. Okay. And then there was kind of radio silence for about 4 months. And I think I know why they've been silent so long. And that's what we're going to explore right now of what's been going on. And during that same period of time, I was, let's say, a little bit silent as well. And then a few things happened, and basically, so here I am. I'm back. But I have a new nom de guerre. So I was there all along. It's just that most people probably couldn't find me. And as you can see, it's more or less my daily musings about the humanoid botanical garden. And that botangelist is basically a portmanteau of a botanist and an evangelist. the humanoid bot space. And during that time, I had a chance to do a couple of deep dives and start putting some posts out there. And the first big post that I kind of put out there in that time was one about the hips. And this is going to be very important to everything else, all about the hips and what's going on there. And we're going to be taking this. And I was kind of surprised at the number of views. I got more views than I normally get. And more important, like the number of bookmarks. This has like over 600 bookmarks, which tells you that a lot of people really liked it. And a lot of it was people in China and India and the US and researchers and everyone else that were reaching out to me. That was rather a surprise kind of understanding of what's going on.
Yeah, it was a whole thread, and you explained and taught us so much, which you'll share today about, hip design. But I mean, it's so critical for a humanoid bot, right?
Absolutely. Absolutely.
Yeah, so this it was so good. It was a good thread. Yeah.
And we'll give, and I won't do the whole thread, but I will set up enough that will make sense on what's going on here. And then I also did a similar thing because the pressure was on for the waist, didn't do quite as well. And then I did another one examining the human gait, which seemed like no one watched at all. So, and then, started going and looking also a bit more at what I call the kidney waist. So some of these waist designs have the actuators actually at the kidney. And no one has a name for it. So I decided to give it a name. I call it the kidney waist, and I end up showing exactly how that actuator works. So if you go there and through it, you'll find a lot of the posts I've had in there. And I also was involved in this article, and that the author of this article reached out to me a few weeks before he put it and just asked me for some of my thoughts. And when the article came out, there was a few factual errors in there, and I felt obliged to kind of go and fix those. So I also have a very long post on that. And that resulted in me also doing a collaboration video with Marwa on her Soft Robotics podcast about the great rotary versus linear debate, because you can't answer this question about the roller screw that you're going to need in the bots unless you answer the question of rotary or linear actuation that's going on there. So that's like a super big deep dive that's going on there. I think that may have got then also turned, well, basically this got turned into a video, and then I've had some other videos that may have got turned back into posts, and I haven't quite done it then, talking about the shoulders, what's going on there. Very little innovation in the shoulder, it turns out. And then also, if you've ever heard the term singularity come up in robotics, I give a real deep, nerdy dive here also in the singularity that will help people understand what's going on there and why that's kind of a worry. So if you want to get good background, we're going to do that. And the first place we want to start is this post I did called All in the Hips. And I was just kind of curious to see what the design space was and what the designers were thinking about the hips, because it was clear there wasn't just one design. There were several designs going on out there. And before we can go in there, you have to come up with a taxonomy for the hip. And to do that, we have to understand a little bit about hip kinematics. That's really quite simple. The first thing is that biomechanists refer to the motion, basically swinging your legs when you're walking, or if you're kicking, as flexion. And when it goes back, extension, but we just call it flexion to keep it easy. And there's ab and adduction, which is the motion of either crossing your legs or spreading your legs. And finally, there's rotation, as you can see here, that would make your knee kind of point in one direction or another. And the thing about these is that the hip is actually a ball and socket joint, but the humanoids are not able to actually do a ball and socket joint. So what they end up doing is they do a serial stack actuators, and that you can organize those in any order that you want. So we have these letters FAR. There's basically 3 letters. 3 factorial is 6. There's 6 possible combinations that we can organize these things. So that means the design space is about 6. And you'll see that some of them have been explored and some not. And the question is why. And you notice there's actually a 7th design space, because we have FAR. So that's going to be flexion, abduction, rotation. And another one, which is rotation, abduction, flexion, which I call RAF. So you get FAR and then RAF. And then there's another version of RAF, which is using a parallel actuation, but basically it's the same idea. And then there's also the TSLA bot design, which is ARF. And you'll notice that the more popular ones are, if you look at the design space, everyone is trying to go to the one where flexion is last. And that makes sense because it's the most important movement And what you want to try to do is reduce the amount of mass that's underneath that actuator. So you want to try to get those other two before. So everyone's trying to figure out, how do we do that to get that down to the bottom so we don't have to carry that mass around? And if you look at like all the bot configurations out there, which is sort of what we're seeing up here.
How many companies? There's 17 companies here, 17 robots,
and
right?
there's more. It's not, let's say, super exhaustive.
17 is pretty good.
1X is conspicuously missing because I don't have X-ray vision and I can't see through the cloth. And, I can speculate. I suspect they might be a FAR design, but maybe not. So I couldn't really put them in there. And there are obviously some others like that I didn't include at the time. They probably should have, like Nura and a few others that have come up there. But basically, this is a sampling of the major ones that we were able to track. And we can see, if we look at like all of the designs that are out there, there's quite a lot that are doing the same as the Tesla bot, the ARF. But what's interesting is if we look at the first generation design, so just look at everyone's first attempt. Everyone was trying to get deflection at the end, but you see most of them went with ARF. And there was only one in their first design, and that was P&D Robotics that went with the FAR design. So the Atom is the only one that went with FAR, and everyone else was over here. And then when you look at what happened in their second generation, you see they suddenly moved over to FAR and everyone abandoned ARF. Now, this doesn't include all the bot companies because some of them have not come out with the second generation yet. And for instance, P&D Robotics is not over here. They don't have a second generation. But a really interesting thing happened in that post a few weeks later. I'm looking in there and I see this.
That. Yeah.
And I was just stunned. P&D Robotics
bone and socket.
Ended up looking at that and replied that we are bone and socket designed for our second generation of Atom. So they're not going to be FAR, and they're going to be something that I've always hoped someone, and they mean ball and socket.
I was going to ask you that, right? Yeah, be as humanoid as possible.
His English is way better than my Chinese. Okay, so I will give him a pass if I think he meant ball and socket here.
Gotcha.
So this is going to be interesting. I have no idea how they're going to actuate it, and I can't wait. And I'm surprised that they've already gone out and announced this, because to me, this is a very big development that'll be very interesting. They've been one of my favorite ones, as you know, because they seem to be thinking out of the box. They're not copying anyone else's homework. They're looking at what other people are doing, and they're innovating, coming up with other stuff. So I really like following what they're doing, and so this is exciting for me. I can't wait to see what they come up with. Okay, so the conclusion. And I put a post out last week that was like mostly well received, but I think a few people got triggered because they didn't understand the point I was trying to make here. And that I'm kind of being a bit jocular here and just saying that, Optimus will suck at soccer. And of course, a lot of people, who cares? And it's like, yeah, exactly. Who cares? But what we're going to do is we're going to point out some of the trade-offs that happen with these designs and things that you may or may not be able to do. So let's use this and really the reason why I started thinking about this a bit more. And the first thing is that back in April, Humanoid Hub posted this video here from Booster Robotics of showing the booster bots playing soccer or football for the rest of the world. And so here it is. And if you kind of watch it, Herbert, what's your first impression about their soccer skills?
Awesome.
I mean, it's okay, but it looks a bit like kiddie soccer, doesn't it?
Sure. Yes. Yeah, of course.
And part of the reason is because of the way they're kicking. So do you notice how they're kicking?
Yeah, straight on.
Yeah. So the thing is, if you
this guy.
If you look at this right here, so you actually see there is someone on their team in the development team that actually knows the proper technique. Now, it may not be perfect technique, but it's considered the proper, and I'm going to put quotes around that, proper technique for being able to kick a soccer ball. And that is, you want to use the side of your foot. So we're going to see this again and again. So you can see how he kicks it, and you can see that the bots are always kicking it with their toe. So I kind of said, well, okay, if they know the proper way of doing it, is there something wrong with the bots that they're not able to do it? Is there some mechanical restriction or something like that? So that was a big question. So you have the proper technique here, thumbs up, and this is the wrong way. And it turns out that this is called endole, at least in Swahili slang, as I learned from Professor Otinga Mare from Nairobi. He says that's what they call it. And I checked it out in Grok, and sure enough, it's endole. And so anyone who is a soccer fanatic knows you don't kick with your toes. You want to kick with your side. Okay.
Right.
So the exploration is like, all right, If we look at the taxonomy of this bot, Herbert, what do you think it is? Do you think it's ARF? Do you think it's RAF?
It looks like the Tesla bot. I'll say ARF.
You think it's RAF? Okay.
ARF.
ARF. You think it's ARF? Well, it's actually FAR. It's FAR. So it's very much like the Unitree G1 and the others that we've seen. That right here, the red axis here is your flexion right through there. Okay. And then the second axis here is the abduction right there. And then right down here, we can see where that actuator is for rotating. So that's where everyone's kind of moved over. And I look and say, well, wait a minute. If they've got that rotation, they can rotate their foot and they should be able to do it. Yeah. And now comparing this to the way Optimus is you see, we've got the abduction first, then the rotation, and then the flexion. And this is kind of the problem, is the fact that the rotation comes before the flexion. All right. So at this point, I'm going to stop the presentation, and everyone, including you, Herbert, has to stand up, and you're all going to become biomechanists, because you're all biomechanists, because we can study our own bodies. Okay.
Okay.
And what I'm going to do is I'm going to go ahead and take my model here. And this is what we want to do. So the idea that if you're going to kick the soccer ball correctly, you need to be able to take your foot and rotate it something like this. Yes. Now attempt to rotate your foot and look down there and tell me how you did that.
Look down there.
Yeah. Okay.
How did I rotate
How did
my
you
foot?
do that? How did you rotate your foot?
I used my hip.
Yes. Very good.
Turn.
Okay.
Yeah.
Now a lot of people are going to think that you can rotate your foot like this. Now on this model I can, but when you try doing it, you realize you really can't. You have a little compliance there, but you really don't. Yeah. And that's why all of the bots that are out there, humanoid bots, don't have that rotation on the foot. They have, the flexion up this way and the rolling back and forth, which ironically my model can't do, which we all do when we twist our ankle. But you don't really rotate it that way. And you're not doing it below your knee either. No one can do it below your knee. Again, you have some compliance, but if you do it too much, you're going to tear your ACL, your PCL, and your MCL. So you don't want to do that. So the way you do it is that you rotate your foot around like that. Okay. Now, because we have this ball and socket joint and the way our flexors are set up, our flexor muscles,
I see
that it's very easy for us to kick in this direction. So when you rotate that and try swinging your leg back, isn't it pretty easy?
Yeah.
Do you find it? Now, try kicking in the direction of your foot. You can do it, but it feels a bit weaker, right? You don't have as much strength in that direction.
I use my knees.
Yeah, you can use your knees, but if you try feeling your maximus gluteus starts burning when you try doing that, because you're trying to get the abductors in there. So sure, I'm sure some athletes can strengthen and everything else, but primarily the power we have is this way, because our actuators, in a sense, are designed, the flexion is really defined in this plane. It's not defined in the plane of the leg, it's defined in the plane of the body. That's how you want to do it. So that is sort of one of the reasons why it's important to have the flexion as the first axis, which is what a lot of people notice. If you wanted to play soccer, and again, in the factory, I'm not sure that we necessarily wanted to play soccer. So we can go back to the presentation. And what I'm now going to do is I'm going to demonstrate this using a little virtual robot I have that I call Decimate. Mm-hmm. And this comes from my fictional company called Decision Technologies. Mm. And it stands for the Domestic Environment Cleaning Intelligence Multi-Action Task Expert, Decimate.
Okay.
I think it's just an awesome name for a domestic robot. I'm sure we'll sell lots of them. Well, what's so funny, Herbert? I mean, it's a mate, right? It's a decimate.
Yeah, he's gonna decimate me. Okay.
Okay. All right. So on the left hip, I have an ARF design, very much the way Optimus is set up, with the flexure down low. And on the right hip is where I have the normal FAR design. And so we're kind of comparing the two, and we can sort of see what happens, that this is what it's like swinging when you have no rotation. So if your toes are pointing forward, you see they both can swing properly. There's no problem there. But when you decide to rotate your feet, then that has to be done with a rotational actuator there. So now both the feet are that way. You'll see with the FAR design, all I have to do is bring in the flexure, and that's it. It swings right through. But, you see that way? You see, it's really hard with the flexure to be able to do that, to get it to kick that way over. It gets a bit complicated. Now, of course, it's a little bit more than that, is that you also want to put in your knee bend. And so that's also going to require maybe a little bit of abduction there to get that. But for the most part, it's still the flexures that are doing all the work to come through. And we can attempt to do it here, but it gets really convoluted trying to get the abductors in there. And so you can organize that. And this is something we're going to point out as we move along. So here's a short clip that we've received recently of showing Optimus dancing. And the reason I bring this in there is you can kind of see it's almost kicking that way. You see when its toes are out in the direction, you see how it has to kick kind of straight out. It's not attempting to kick forward, as it's kicking side to side. So it's almost proving my point. So I just wanted you to see that, the virtual model is one thing, but if you look at the real model, you see it's doing something very, very similar. Okay. Now, I did receive a lot of feedback here, and here's one from someone who, is a PhD student and thinking about it. And I want to point out that this is not quite right. Okay. This kind of coordination is some simple kinematics that can be learned trivially. So in other words, he started arguing, you just coordinate maybe your abductors and your flexors and everything together to be able to do it. And it's like, well, depending upon the order of operation you have, you may not be able to get out just by software. Sometimes hardware design is just going to limit you. And again, we'll sort of show you what's going on here with Decimate. So the idea is that this green actuator up here, which is your abductor, which is coming in first, if you try using that to get it to swing forward, you'll see how it comes way out. And then suddenly it comes in very close together there. It kind of self-collides. It's really tricky to do that. So be careful. Software is not an out for everything. Sometimes, they use software to fix a problem on the Hubble Space Telescope and a few things like that. But in the end, build your hardware correct.
Gotcha. So this is so incredible. I love that you showed that.
The reason I masked this before, you didn't see actually what was going on in the hips, is that this is the normal thigh gap that you see in Optimus when it's standing straight up. And now after that ballet pose, where it came in there with its feet, you notice the thigh gap just collapses, just like what I showed you. So this is the problem. It's going to be very hard for it to come through. Now, remember what I just said, that if you try pointing your toes to the side and try kicking, you cannot kick with authority. Your kick is going to be straightforward. However, it's the opposite for Optimus. Optimus can kick another way. So we really have to start thinking about what's proper and what's not proper. And we'll get in there. But before we do that, I talked about before that Optimus will suck at soccer. And it's not because of a problem of getting the organization of your joints wrong. It's a missing joint. So to do a proper header, you need to have the neck bend, which Optimus doesn't have. Okay. So if it wants to be the GOAT like Ronaldo, they're going to have to put that in there. Okay. So that's just a missing joint. It's not an organization. Most of them. There's very few bots that do that. I think. Yeah,
they're missing it because it's one less actuator is too expensive.
Yeah. I know Apollo does it. I'm not sure if Iron does it. Phoenix from Sanctuary, but most of the others no. You almost don't need it. Some of them are putting there only because it makes it look more human-like. It's not because they want to be able to score headers. And of course, you don't necessarily need to score a header, but if you really want to get that critical one, maybe you do. So. A lot of people did an interesting thing. They were like, okay, am I actually right? And they asked Grok. And it seems like Grok backed me up. And then there was this one here that was very interesting. And I checked this out myself since Grok generated it. And then Grok told me that there was no such thing as the International Journal of Robotics. And as a matter of fact, the OP said he wasn't sure if it was hallucinating. However, Grok did feel that there was enough academic support out there from it to say that is kind of a proper design if you're going to have soccer playing bots. So it may be that it just kind of confused everything. Again, if you want to go ahead and check the different AIs out there and see if they kind of agree with it. All right. So part of the reason we're having this problem is that, and this is going to be with all the bots, is that this is how the human anatomy works. We have a ball and socket joint, and this is how we do those 3 rotations.
Right.
It all happens right there. It's concentric right there on that point. So all these intersect right there. So now if we look like an example of an FAR design here, we'll see, well, it looks almost the same as a human, right? Because look, all of the rotations are concentric. So therefore, it must be exactly like a human, right?
Mhm.
Well, you overlay them and you begin to realize, we left out,
I
the
see.
fact that you get this femoral neck here, and the fact that the rotation
Mm.
along here in the human is not along the femur.
Mhm.
Okay, so it's not coaxial with the femur. And so you see, actually, the only rotation that is correct with the FAR design is through the flexure. The abduction and the rotation are actually not in the same location. So they're a little bit different. So we should expect the robots will be able to mimic us, but not perfectly.
Mhm.
It just gets a little bit worse with the ARF design, okay? Especially in the case of what Tesla has done, is because the flexion down here is so far down. So they have, a big offset here and a much bigger offset down that way. So that leads to some potential problems of being able to do it. But the question is that what it's supposed to do? So, another reply was that this shows a lack of imagination, in my opinion. Maybe. I agree with all you've said, but that only proves that Optimus will suck at mimicking how humans kick a ball. And that's exactly the point I was hoping everyone would pick up.
Exactly. So let me pause for a second.
Mm.
I one of the ways I understand that bots are being trained right now is not only through simulation but also through reinforcement
RL.
learning, right? Which
Yes.
means that I'm a human, I'm wearing all these equipment, and then I do the move, and then I'm going to get my bot to copy the
Well,
move I make.
that's more imitation. The reinforcement's a little bit different.
Okay,
Yeah,
so
we're
imitation.
We're going to get
that's the word
yes.
I'm saying. So if it's imitation, then the closer that the body of my body matches the humanoid bot body, then it's a lot easier for that bot to copy me. But if if I have like three segments in my finger, and they have 3 segments, then they'll copy it exactly. But what happens if it's different? And so Optimus is very different from a human, and all of them are because they're not ball and joint. And so then how does that bot imitate my movements like you just showed with the talker kick? It can't do it.
Yeah, exactly. And this is kind of what's being pointed out. So if we go along here, the other point they make, that doesn't mean it can't kick a ball on its own by leveraging other clever ways to use what it has, no matter the limitations.
Exactly, true.
Just like a person without arms can train to use their legs and feet in unusual ways to do stuff that even people with both arms couldn't hope to accomplish. And I absolutely agree. And that's why I said, that's why human priors could be detrimental to RL. And we're going to get into that for a second, as it may confine the solution space. Assuming it should kick the ball the proper way, prevent inventiveness.
Yeah.
So that's the whole thing, is that we're trying to, and that's what imitation learning is kind of doing, is you're showing it the proper way and you're not giving it any inventiveness. It just has to copy and do what you can, even if mechanically you can't do it. We kick balls with the side of our foot because that is what our mechanics prefers. Yeah. Our mechanics prefer. So what that means is that Optimus won't be able to copy us. And it also means the robots with the FAR design won't be able to copy Optimus. So Optimus might have an advantage on the soccer field because they're not expecting this powerful kick coming from 45 degrees, even if it's indole, okay? It doesn't matter. The whole flexure is going to go in there. So that means we sometimes we have to be very careful how we train these things and allow them to do that. And that's where I come to this next segment about RL locomotion. And so this is something that I think it was back in March that Figure released, that they're using reinforcement learning for locomotion and the improvement that it made overall. And part of this video segment was also a post from Brett talking about the fact that they had a white paper. And if no one's seen the white paper, go to there and read it. It's on the Figure website, and they explain exactly what they did in there. And probably just myself and I think Chris Paxton read it. I'm not sure.
Sure. I read it.
And so, so this is an interesting post, because when I read it, I was like having the same thoughts. And then Chris basically posted this before I had a chance to. And then if you read down the part that he highlights, it says, this includes walking with a human-like gait, with heel strikes, toe offs, and arm swings synchronized with leg movement. We inject this preference into our learning framework by rewarding the robot to mimic human walking reference trajectories. Okay. So that's what you would consider a human prior that you're going ahead and putting in there. And when he read that, he kind of came to the same thing, wondering that I was like, is this actually going to be more optimal? No matter how much these robots look human, they aren't.
Yep.
Motors are not muscles. Metal is not bone, etc. It seems artificial and suboptimal to reward human motion for a general purpose robot. Okay.
Yep.
Now, that's a very, very good point. There's a couple of reasons why they're doing the human priors. And that is in the first paragraph is what they say here is like, over time, we want our robots to move more like a human through the world. That's the whole idea of the humanoid is it wants to be familiar. My feeling is that, and in many cases, reinforcement learning requires a lot of computation. And if you just let it figure out on its own, you don't have enough time. So what you do is you inject those priors in there to help it come up with a solution a lot faster and a solution you want to have. And I call that priming the pump. You just kind of put in there, just make sure you get the answer a lot quicker. Chris would see that more as like poisoning the well. And I think he's right, because when they have time, they should go back and completely get rid of it. Make sure there's no echoes or anything like that in any training sets, and let it figure it out. And if it doesn't walk anything like a human, if you get a silly walk or a goofy walk, some kind of crab walk or something like that, then that means you need to rethink your hardware strategy. There's something wrong. Use that as a way to iterate on your hardware, because we do want it to walk like humans. If we want it to walk like humans, we better figure out what's wrong with the hardware and not constantly do a software patch. So yes, with software, we can do that, but it may not be the way we want to do it. So that's sort of the way RL is working. And it's a very good, strong point that Chris is bringing up here that I want everyone to sort of understand. Okay.
You know that today Elon was interviewed, and he actually said that they're working towards a model where the bot will learn and play on its own and figure things out on its own, like a child learns on its own. So instead of telling it, here's what to do, you just leave it alone and let it figure it out on its own. So maybe that's where they're going to head to.
And that's real reinforcement learning, because imitation learning is that there's no inventiveness. It just basically repeats what it's been shown, and it's through reinforcement learning and certain reward functions you put in there that it actually gets to explore its space. And right now, it's really hard to get it to explore its space in the physical world. So we have to do it in the software world. But eventually, when it's smart enough, you can then start having a playroom where it really goes in and starts, they call it a romper room, whatever, where they start playing together and learning collaboratively that way. But they're not quite there yet. Everything has to be kind of bootstrapped. So we had this post come out a few weeks ago, and it broke the internet, right, for a couple of reasons here. And as we can see, Optimus is dancing and dancing pretty well. And the result of this is that before I actually decide to break this down, we need to go
back to the future.
Use a little bit of time. Well, back to the future, back to the past, whatever. We need to do some time travel here. Okay, let's just do some time travel. Okay, so I'm going to go all the way back to December 9th.
Right.
Okay. And I think you may all remember this. Let me see. Do I have the video here? I thought I had the video. Oh, yes. I think we remember the daily walks that Optimus was doing. And I don't have the video. I thought I loaded the video here. Anyway, this is what Milan posted about that at the time. And you probably narrate better than me, so please read this whole post.
Okay. It says, this is Tesla's where real world AI is happening. These runs are on mulched ground where I've myself slipped before. What's really crazy here is that for these, Optimus is actually blind, keeping its balance without video. Only other onboard sensors consumed by neural net running it in 2 to 3 milliseconds on its embedded computer. More exciting work happening on adding vision so it can better plan ahead, making the gate look more natural in such rough terrain, making it more responsive to velocity direction commands, learning how to fall to minimize damage when unavoidable and stand back up. Yeah.
And read the last paragraph.
Join us to work on fascinating reinforcement learning, imitation learning, foundation nets for robotics.
Okay. So, what was your impression? How was it trained to walk in the mulch?
How was it trained to walk in the mulch? I mean, first of all, no eyes. So just somehow walking blind.
Do you think it was heuristic? I mean, it was using neural nets. How was the neural net trained?
Oh, I would assume it's in. Well, I mean, they said that it was. Uh, I don't know how it was trying to. I guess I'm assuming it's real world AI, so he's referring to neural nets. Yeah.
We're referring to neural nets, but we don't really know how it's trained. There was
Mhm.
there was a mention of RL, but you'll notice it's in that section where
Yeah.
they're recruiting for everyone. So
Right.
if you
Right.
read it really quickly and you see the reinforcement learning, you may jump to the conclusion. And I
Right.
think John Gibbs and I may have, because I checked with him, and it's like, wait a minute, after we saw that, didn't we think that that was probably RL and they were starting to do it? He said, yeah, you think so at the time, that it may have been reinforcement learning. And the assumption is if they're doing that, we should start seeing a lot more updates since then. And remember, this is December 9th, 2024. And we
Mhm.
didn't really see anything major coming out of Optimus since then. I mean, there were a couple little updates, but they were really not about Optimus. They were just Valentine's wishes and a few things like that. So it wasn't until April 2nd that we got the first update. And that was this.
Right.
Okay. So there's Optimus
More
walking.
human-like. Yeah.
More human-like, rather interesting to see what's going on there. It's not too bad, but still it was walking pretty well before. I always thought that the gate, it always had a nice kind of sachet, the way it moved around. So, but this, we weren't quite sure what it was. And then sure enough, our latest walk, straight knees, smoother knee to heel, gait and arms,
Yep.
just chilling around. Entirely trained in simulation with us. So that's like the first time it's confirmed they've done RL.
Mm-hmm.
And so what I think is they've been trying to get RL to work over the intervening 4 months. And it's only now that they have it. So that's April 2nd. And we didn't really hear much since then. Now, what I did is I went through this video, and you can do this at home. And I looked at the very first step and got the timestamp on it. This is my timestamp. You're probably going to need a different one if you download it from X. And then I counted how many steps. There was 21 steps over this amount of time, which resulted in me creating this spreadsheet where you put the start time, the end time, get the total time, count the number of steps, and then you have to kind of guess the step size. And I'm guessing this is like probably the biggest step it ever took. A lot of them, it was just like a little bit in front of the other toe. So maybe 16 inches, if you want to put in 18 inches, whatever. The number of steps per second, feet per second, everything. And in the end, we'd get 1.5 miles per hour, something like that.
And you said humans are typically 3 miles per hour, correct?
3. What you want for the meters per second is 1.2.
Okay.
And so it's about 2.5 miles per hour, something like that. So you almost need not quite a doubling. So you're getting close. All right. So how does it compare to this one? So we have this video that goes back in October, where again, it looks kind of smooth, maybe a little bit slow. You see the steps might be a little bit closer together, but if you give it sort of the same step size and everything else and do the same exercise that I did here, you end up also being able to come up with some numbers. And so based on that and using that, I get almost, so it's maybe a little faster now, but it's within the margin of error. And it just comes down to how big you think the step size is. So maybe it's a little faster now. Maybe you get a 10% improvement or something like that. But you see, there's nothing amazing about the speed. It just looks a little bit different. And they still have some improvements to go ahead and do in the speed. No doubt about that. So again, this is something you can do at home. Okay. Now, also on April 2nd, Ashish also confirmed, learned an RL in Sim, deployed 0 shot to real. So for them, that's really the big deal. It was 0 shot. That you were able to do it in RL, deploy it on the bot, and it worked. Okay. Now, this is a rather interesting point here that I think no one's really picked up on, but I think is very important. We are planning to extend our RL Sim training to manipulation in the coming months with the 22 DOF hands. Initial results will produce dexterous robot manipulation. This is why we haven't seen any manipulation. They are probably able to do things a little bit telerobotically and stuff like that, but it's not really ready to do. Maybe there's a little bit of imitation learning, but they want to extend it a bit further. So my suspicion is, basically this is planning, which means they maybe haven't started yet, and it's going to be taking months. So maybe sometime mid-summer, end of summer is when we might start to see updates of manipulation tasks, because we haven't seen that yet. Okay. But they are very excited about, my team is also building a generalist robot policy by leveraging robot and generic internet video data. I think that's exactly what we just talked about, what Elon said today.
Elon said another thing he said today is that they're feeding it videos from YouTube and others, and then it's able to mimic it.
Yeah, exactly. That's what's being said right here. Generic internet video data. So there's confirmation on that statement. Both are critical path to general robot intelligence. Reach out if interested. So every one of them is like, we're hiring if you want to be part of the team. And just so you know that he's just not some guy. He's leading AI there. So if everyone wonders who he is. And now then, so again, this is what we saw of
last week. You said
or actually April 2nd. Okay. So this is
April 2nd. No, this is last week.
This is April 2nd. Not last week, because you see he still doesn't have his guards on. So this is the first one, and he still has got the covers on there. But then, after that came out last week, Milan said, more coming shortly. The team has been working very hard in the background, entirely trained in simulation with RL. Once again, confirming that. Whereas before, they weren't like talking about it again and again. It's very clear now. Many optimizations and fixes have been put in place in our sim to real training code. I'm sure there has. The cable is there in case of a fall, not actually holding the bot, since this is an early result, which will get more stable very quickly. So he says more coming shortly. So that was May 12th. Evidently shortly means, okay, before we get to that, sim to real for Optimus, getting really good. It's quite handy to have more than a decade of actuator design in-house. Okay. Now, to me, this post from Julian, who is Tesla bot AI lead, is insightful, because I sort of talked about, and we're going to see a little bit more, that the issue of getting the simulation right for RL and this whole rotary versus linear is that when you have linear drives, it's a lot harder to simulate.
Yeah.
So in order to pull this thing off, you need to have a really good RL environment that includes being able to simulate it right. And be able to simulate it right means you need to have people in-house who actually understand the actuator design, how it works, so you can model it correctly. So they're probably already modeling it to design it in the first place, and now they can take that and put it in there. And it's not just the actuators themselves, but also the gearboxes that are going to be in there, the linkage mechanisms, getting all that right in order for the sim to reel to work. So this was one of those things like, I bet that's one of the things that just made it very hard for them to get to this level when everyone else seemed to be way ahead, that you needed to do that. Okay. So now this comes out on May 14th. So
2 days later.
Yes. And this is where we see a variety of different movements here, of different dances. And the one thing you'll notice are different times of day. They're in different locations. And what that means is they probably trained it up with one set of dance routines, downloaded it, tested it, went over, did another one. So that means they are able to get these moves, or, they may be getting some rigging from, Blender or some others to get some idea what these dance moves are, and then put them in there and then get it to learn how to do it. With this actuation strategy, and then download it and go. So you see, it's really pretty impressive. And what are what the takeaways here? First is that it's full body control. There's no doubt about it. This is the Gen 2 bot. Let's be clear on that. It's not the Gen 3. But right here, some of these steps, they're pretty quick. And I just wish they'd send out one more video, and that is Optimus walking now with RL, a new update, because April 2nd, they showed it, but I think that was like, they just got it working. It was there. It was something worth posting. And now we're a month and a half later, and we're getting this, which is showing that, the pipeline is working pretty well, and that's moving quick. So I'm trying to extrapolate. I'm assuming it can walk 3 miles per hour now.
Whoa!
But I can't confirm that.
Wow!
Just because, look at that. Look at the size of the step. Look how big those steps are.
If
those are longer steps,
why
they're very quickly.
Walk 3 miles?
Right. So please, Tesla, if you're out there listening, that's all I want. A really prosaic update of it just walking normal speed. I don't care about running. I want to see it actually walking at the speed that we probably know it can do. And that will tell me that, okay, you're ready. Because it's very clear it can change direction really quickly. That's
Yeah.
always been the problem with many applications, is that they pick up the box and then they have to turn around to walk in another direction.
Yeah. What
And
did you
that's where
call
all
that?
the cycle time
Shuffling?
is lost.
Yeah. The
Yeah, the
shuffling where the
shuffling.
feet
In this
moves
case,
one
look,
foot, 1 foot, 1 foot, 1 foot. But here now it can actually just move its hip and flip
it
over,
can
right? Just
pirouette.
like
It pirouette. Yeah,
pirouette. That's
exactly.
what it is. That's
Exactly.
what I do.
Now my whole complaint about it can't do soccer, it doesn't matter. It can still use that rotary actuator. You see that rotary actuator that's there? So what if it can't kick straight? It's able to turn around really fast in a very enclosed in there. So it'll pick up something, it'll turn around and go. It'll pick it up. So this tells me, yeah, it's able to do those short haul kind of things very quickly when you need to pick up something, go over and drop it off. But I need to see the update to know for sure.
Sure. But even more important that
yeah.
I think, right? I mean, I know you didn't just go past it fast, but it's the R2Sim program that matters most. And that's why I don't care that they took months to figure it out, because it's like once you build that platform, then anything you show it, a video, one shot, boom, it can do it. That's the platform was needed to be done. Designed to do you think Gen 2 is going to be, Gen 3 will be the same design as Gen 2? I mean, could it be that they changed the design completely?
It could be. And of course, the thing is you have to retrain it, because then, the neural nets are really specific to a particular model and everything else. But you're seeing they have the pipeline, they have it figured out. And the reason why they wouldn't want to make major changes is like probably getting in the physics in there was like really hard to model it, and they have to do it again unless they've figured out how you just put in a couple of parameters. Maybe they have some way to automate it. Now, what I'm going to do is I'm going to steal an analogy that James Dalma uses, and he talks about the foundation. A lot of time when you're looking at a construction site, you go past it and it looks like absolutely nothing is happening. It's because they're digging the holes, they're laying the foundations like that. And once the foundation gets laid, suddenly the building goes whoop, up so quick you can't believe it.
Fast. Gotcha.
Yes. So 4 months, they had to build a really big foundation because they probably were able to get around to it. And now we're seeing. And so I kind of joke that while this is zero shot, it's not one shot. There's multiple shots, but it's not multiple takes of the same dance routine. Every one of them is different. And that's why there's multiple shots. Even though you don't see a long take, it doesn't matter. It's like they were able to do that, and it's going around without the cables and everything else. And I think, again, it was only May 13th. So evidently a short time was one day. Here's a little bit more, no cables this time. It's all real time. Zero CGI, fully learned in sim and zero shot transfer to real. Okay. Besides the fact that it's fun, we had to make significant improvements to a robot model in sim. I can believe that. Domain randomization and other techniques, which will directly transfer to more practical situations as well. Robust walking and agile full body control in general. So the full body control is amazing. There's no doubt about that. And then there's the domain randomization. What does that mean? It means every actuator is not the same. That's what it means, is that even... So you have to make sure in the RL from bot to bot, exactly. Each bot's even within the bot, the morning and the afternoon, it's going to be different from, when it warms up, the temperature, there's going to be over its lifetime. So what you need to do is you need to know that, well, our actuators have this kind of performance profile. It's going to be like a Gaussian profile or something like that. So they're going in there and making sure it's able to adapt the fact that, hey, that actuator is getting a little bit weaker right now. How do I compensate for that? And that's what allows robust walking. And this is why you need to use RL over imitation learning, because imitation learning, it doesn't know how to really respond to things that are not in its training set. The idea of RL is it can generalize a little bit better and figure out how to do the recovery. So it's very important to do that. And then the other thing, we also learned quite a few things on our hardware and tuned our power profile. I bet they did. And it's really good that they learned quite a few things about the hardware and what they need to tune in there. I'm wondering if they're learning some things about the kinematics that they may or may not want to change. Because, okay, I'm dogging them jestfully on I can't play soccer, but they don't really care.
They don't care, but it also could be what you just said, which is they learned after they did this, they realized the limitations of the current hardware. And maybe they're now tweaking it for design 3.
But again, I mean, this is, let's say, most of the comments I got was, who cares? It's, it's not supposed to play soccer.
Yeah,
exactly. Exactly. Yeah. As a matter of fact, and this is something that Robert Scoble told me, is that Tesla engineers said that Optimus is actually Optimus feet are actually optimized for standing, because that's their
Smart.
expectation. It's going to be spending more of its time standing. So they're
So
more
smart.
worried about that than running or playing soccer or something like that. So it's got some optimizations to help it walk a little bit better, but they're realizing that based on their use case. So they're looking at their use case. What's our use case? Let's optimize to our use case. So that's what I'm pointing out is engineering is a trade-off. Optimization, everyone thinks optimization is perfection. It's like, no. Optimization is the art of compromise. You are compromising constantly to try to find what is the best overall. But any one individual system may not be perfect. So you have to make sure it fits the use case and you're not trying to do more than you really want to do. Remember, they famously said no faster than 5 miles per hour. Okay.
Yes.
So they were designing to that.
Yeah.
All right. Again, Ashish says, here's some more with music. All these are the same pipeline: RL training and sim followed by sim to real, zero shot. Yeah. And then Ashish concludes with, our pipeline is relatively robust and requires minimal tuning per dance. This allows exponential scaling to new behaviors. So this is pretty big. And again, it shows that the foundation has really been laid well, that more things are going to come a lot faster. Again, I'm hoping to see some really interesting walking videos, maybe, speed walking outdoors over rough terrains and everything else that will sort of show the robustness of the system that they have. And that way we'll have a better idea of what the actual speed is. Now, one other team member, again, Julian, put this out as like, more dances, all learned end to end, zero shot from sim to real. RL is back in here to stay. And that was a very curious comment there, that it may have been that there was a debate on whether RL was the way to go. So it could have been they were trying to use imitation learning or some other method to train those nets, and maybe an internal discussion, but now they're convinced. So again, when you look at this explains the 4-month kind of absence of what's going on. And now there's that possibility that we're going to see things really ramp up from here. It may be a little bit delayed on the manipulation front because it took them a lot of work to get the actuator models correct to be able to do the walking. Now they're going to have to do that hand. And that's a very complex hand, 24 actuators, even those 22 degrees of freedom. And they have tendons in there. And so the modeling of that's going to be rather tricky. But if anyone's up to the challenge, I'm pretty sure these guys are. Okay. So, and then one last thing is that, again, I was sort of talking about this is that one of the issues this is a post that came from Jim Fan back in January when Unitree showed their RL walking and everything else. And so he was reverse engineering that particular demo, not the Optimus demo here. And this is a salient point that I've stressed again and again and again, and I really like, is that simulation used to be an afterthought. Now it has to be part of hardware design process. If your robot doesn't simulate well, you can kiss RL goodbye. Hardware simulation co-design is a very interesting emergent topic that only becomes meaningful with today's compute capability. So he's kind of intimating there that if you have a really complex kind of kinematic or something like that, it might be a bit harder to get into RL. And I think that's the situation, is that all the bots that we were seeing, and the analogy that I've sort of used is that you have one camp that is like all rotary actuators and another camp which is all linear actuators, and they're kind of at polar opposites. Optimus is kind of at the equator because it's a mix of both that are in there. And so those that were at like the North Pole, if you want to say that's where the rotary camp was, they all were able to do RL really quickly because it was much easier for them to model it, because in a sense, they were almost designed for simulation. And so, we've heard about design for manufacturing, design for excellence, design for maintenance, and all these others. Now there should be design for simulation. And I just wish I had Jim Fan's clout 40 years ago and could have explained that to the robot manufacturers back then. It's like, well, it'd make my job a lot easier with our really slow machines that where they were megahertz processors and not gigahertz processors to be able to make it easier for us to simulate. But it is very important. If you want to get that sim to real right, you need to get the simulation right, and the easier you make the model. Now, eventually it probably won't matter, because the compute will be so good and our physics will be so good. But right now, there are limitations, and you have to respect those limitations. And that's what probably took them a little while to get there. And so that's going to be tricky with that hand. That hand is going to be very hard. we have to be very frank and honest about that, is that absolutely it's not going to be easy for them to put into RL right away compared to other designs. But even then, all the other human hands that may not be using tendons, there's still some complicated linkages in there. There's a lot of physics going on as well. So it's not going to be easy for them also. So again, here's what we've seen of what the bot was able to do. And when it did that, a lot of people noticed this thing.
Yes.
So you remember that if we just go back to it, at one point, there's a frame in there on the very first one where you can see this toe section is pointing up. And there was a big debate on the internet about whether the toe box is actuated and is this new? Okay. So I ended up doing a long post out there about this that I call a big flap over a flap. Okay. It is articulated, not actuated, full stop. Okay. Please, it's not. Why? Physics. Okay. And so I'm going to explain that, and we can go ahead and look at this for a second. And that is, this is just that segment right there. And you'll notice the foot is being kind of dragged backwards. It's doing a moonwalk in a way. And this is the first time we've seen Optimus do that, because normally just walking straight ahead. So the foot is being dragged back. Okay. So what happens when you drag a foot backwards? Well, first of all, it's always been actuated. All right.
Yeah, it's always in there.
They told us back in December 23 with the reveal of the Gen 2. It was always there. You just had, and it's articulated toe sections. It's not actuated, it's articulated. So we knew that all along. And I want you to see what's going on here. And you see that big gap down there?
Yes.
That means like a lot of gravel and other particles are going to get in there. It doesn't close up very well. So you do see there's a gap, and you can see there's an exposed edge there very clearly when you begin to do that. And you can also see the fold that comes in here. And that articulation point is up a lot higher than I thought. I thought it was lower, but looking at this, it's pretty high. Yes, you do see some cables going in there, but those cables are for the foot force torque sensing. It's not for an actuator. That's what that cabling is there for. Okay. And if you were looking, this is back in 2024, in others, and this was like the recent walking videos, we can see the articulation was always there. So you can see that toe box is flexing just a little bit in these different. So it clearly has been articulated for a long time. It's not anything new. Okay. So let's take a look at what it actually looks like. So it's going along, and basically it flexes and then returns because there is some sort of torsion spring in there that pops it back into position. And it's probably pretty stiff when it's down there. So you need a certain amount of force or torque on that toe section to get it to open up, because you want to basically keep it straight. And then the more it opens up, the more it's pushing back, because that's the way a spring works. So we can see that, and this is from the Optimus reveal video. Okay. So this is going back, yes, a long time ago. This is not something recent that I just picked up. That's the Optimus reveal video. If you look in there. All right. So what's going on? And again, why do you even want to have an articulated toe box? What's the whole point of articulated toe box? Well, for the first part is like contact surface area. So, if you have a lot of surface area, you generally are able to generate a little bit more friction. I know physics textbooks may look at it a little bit. The reality is the more surface area you have, the better it is. Okay. Now, if you have a very flat foot, which the original Gen 1 had, as soon as you have the slightest angle, I mean, we're just talking about a little bit above 0 degrees.
I see. Your
whole point of contact is way out here. And we know that's just going to cause you to slip and fall. So if you have an articulated toe box, what you do is that as you are able to do what's called, this dorsiflexion going on here, you're able to maintain a reasonable amount of contact area that prevents you from slipping, that you need as you go to complete your stride. So you definitely need that in there. Okay. Now, let's take a look at what happens here when you drag your foot backwards. So this is like a little simulation I put together showing that you do the dorsiflexion, that it opens up, and now you drag the foot backwards. And as you drag the foot backwards, that's going to want to open up. And the reason is, and we love creating vector diagrams when we're engineers, is that here's your foot, and this is your vector direction is that way. And if you're moving the foot back this way, you're going to end up having a frictional force right there, which is going to be pretty much concentrated at that edge. And you've got this little lever arm here, R. And a force times a lever arm is a torque. And the torque in this case is going to be counterclockwise, which means it's going to open it up. So that's what's going on. That's why you're getting the flap. It's not articulated. Okay, so that's why we end up getting that. All right, now, just to make sure that we understand that this is about as close as we're going to get to confirmation that that's the case, because this was one of the replies that I ended up getting from this post of mine that I actually was kind of surprised to see from Anand. And that is, in articulated toe, even a well-tuned passive one, okay, adds a lot to improve the gracefulness of the gait. It also becomes important while balancing weight transfer and kinematic reach for going upstairs. It's actually obvious when you just walk and pay attention to what our feet do. But we don't think about it
going upstairs. Yeah.
About it most of the time. I reposted that because I'm always telling people we are biomechanics. Study your own body. And I had to repost that because that's exactly what Anand was encouraging everyone to do. That, study it, and you begin to see that and understand, aha, yeah, that makes sense. That makes sense. Well, Anand is not just some guy. He's been on the Tesla bot team since the beginning and with Tesla for over 10 years. And he just recently left for Zipline. So I think that's as close as we're going to get as a confirmation, because usually those team members never comment on anything. And, he's sort of saying it's a passively tuned one. So I think that's pretty much confirmation. It's not articulated. Does it make sense to articulate it? Maybe
actuated.
someday in the future.
You mean it doesn't make sense to actuate
actuated.
Yeah.
Actuated.
It's articulated, passive, but not actuated. Yeah.
Does it make sense to make it articulated?
No.
Maybe, but remember, they're more concerned about it being able to stand than, let's say, do 3-pointers where you're able to like bounce off your toes and everything like that. So, there may be cases in the future, but that all comes with a cost. They always point out right from the beginning, they're trying to reduce the mass, not put anything down at the ends. It's just going to make it heavier and stuff like that. So they're trying to move everything back to the center as much as possible. So you only put it down there because you absolutely need it. And it's like right now, you absolutely don't need it. In our feet, technically our toe box is articulated, but most of what's going on is our muscles are being used more like springs to absorb the energy and put it back in so it's almost passive. It's only when we really want to like jump or we need to kind of get our balance back. But for the most part, a passive system, like Anand says, a well-tuned one will be able to do that for you. It absolutely works fine. Yes. Yeah. And so again, here he is. he was a member of the team, and you can read the post. So thank you, Anand, for
I met him, talked to him at length at the We Robot event. Yeah.
Right. Okay. Now, the next thing everyone's kind of wondering about is you notice the Optimus PFP changed a little bit here. Sort of
profile.
Yeah, the profile picture. Yes. So the profile picture changed, and everyone assumes this is like the new Gen 3 bot. And the closest we've come to seeing it was in the quarterly report was this image of the pilot production line. And we can clearly see it looks different than the Gen 2 bot. Now, the Gen 2 bot is what we're seeing do everything being done. We've only seen release that. We have not seen this in action. So what are some of the changes that we are seeing here? Well, we can see the neckline is definitely different. We can see that they're using the same strategy in the shoulders. It's just the coverings are different. So it's basically the same idea there. It's basically what I call a FAR, also an FAR kind of shoulder. That's the design everyone is using. No one has anything different. But we can see they're mounting the 22 DOF hand here. We can't see enough on whether there's any changes to the hips. I think I saw a couple kind of close-up stuff that indicate to me that they haven't changed anything. They're using the same actuation strategy. The legs back here kind of look exactly the same. So I don't think it's radically different. Maybe because we can see the torso area, they packaged it a little bit differently. So there's no reason why they wouldn't have maybe repackaged things a little bit differently. But I believe kinematically it's the same. Otherwise, they wouldn't be putting all this RL effort in a dead design. All right. Now, again, the hands are not that important to the balance of what they're doing as far as the fingers. Yes, getting the arms out there, ballet, it is very important to kind of get there. But whether it's a 22 DOF hand or 11, it's not going to affect everything else. So long as everything else is very similar, it's just going to be a matter of tweak a couple of parameters because, the actuator is lighter and tighter. So we just need to, again, we've got the actuator design in-house. They can tell us what the new parameters are. We stick it in the RL and then we'll go in there. So I don't think there's much change. I don't call this the Gen 3 bot. I think it's more it's the Gen 2 refresh with the 22 DOF hand.
Okay.
That's more my feeling. It's not like a radical change. It seems to me to be a little bit more of a refresh.
Okay.
And it may have been that a lot of the changes were just to make it easier to manufacture. There may have been a lot of things they learned that are just a little bit tricky to do and for the pilot line. So this is not going to be the one that they're going to scale up really big. This is the prototype production line that they're going through.
Maybe the 2,000 to 5,000. Yeah. But
yeah,
not
yeah,
the
they're going to learn
20,000.
from this, because the first thing they need to do is they need to deploy them and get data from operation in the field to see what the reliability is like. What are all the problems? And then when you get it, you can begin to scale. And that brings up, and it might be a little bit hard. So I put together a quick spreadsheet because there have been some discussions about, scaling and whether we can get up to, 100 million, a billion bots, how long are you going to get there? And there have been some people that don't think you can get to a billion until like 2050, including like maybe Morgan Stanley and others, and those that are, like, say, very aggressive with their timescales. So what I want to do is, like, let's kind of look at it realistically on what it would look like to kind of scale up. In 2023, not just Tesla, but just about everyone else out there easily had 10 or more bots. So order 10. And some of the Chinese may have already had more than that. And then by 2024, clearly they were all in the order of 100. So they scaled about a factor of 10 there. And in 2025, I think all of them are shooting for in the order of 1,000 or more. And it looks like it's doable. They're all scaling up from that. Tesla has made these announcements. There were some recent announcements where people thought it was going to be a lot more, but they're consistent. What Elon did is he clarified. I think someone thought they were going to be like 10,000 a month right now, or 1,000 a month. They thought they were, and it was like, no. We're building for something right now that will be able to do that by the end of the year. And that's completely consistent with statements that were made back in January, that optimistically they would like to, as an internal target, but realistically they know it's going to be less than that. It's going to be a few thousand.
Yeah. Having a production line that's 1,000 per
month by the end of the year.
By the end of the year.
And when they do that, that means you're talking about 2026 production on the order of 10,000. That's going to be possible. So that all looks reasonable with maybe some hiccups. Okay.
Yes.
So now it's still a little bit of effort, but it's not going to be that hard to continue to 10x that for the next year up to 100,000. So that might mean the pilot line goes a little bit faster. You've got to push your sub-suppliers, but I don't see anything in the supply chain that would be an issue, that they should be able to do that. To get up to 100,000. The only reason you wouldn't go to 100,000 is that after either your first 1,000 or first 10,000, you realize the robot design sucks. We got to change it. They already know the robot design sucks. They're already working on probably the Gen 3 and the Gen 4, and they probably already have a notebook full of ideas for Gen 5. Okay, so they're doing that. All of them are doing that, and so by 2027, they're not going to be producing this version of the bot. It might be the next generation, or even one past that, because they found out all the issues, either production or quality issues. So a lot of times they're kind of ramping together. So one of them is going to fade out, the other one's going to come in, but your ramp up will be quicker because you are utilizing the same lines and a lot of the other things you put in place. So it's still possible that they can be around 100,000 in 2027, and then maybe hit 1 million. It's hard at that point to scaling at low numbers, factor 10 is easy. And then maybe as a stretch goal, you're looking earliest 2028 that you hit 1 million. Okay. Not saying you will, but there could be all sorts of hiccups. The hardware sucks. Some issues with the supply chain. The AI just doesn't work as well as you thought it would. So it slows you down. So there could be some speed bumps there. But assuming there isn't, yeah, you could get up to about 1 million by 2028. Then the question is, can you continue that growth rate of 10? That gets a bit harder of being able to do it. So let's slow it down to factor 3. You do that, you still hit 1 billion by
2035.
2035. So, and even then I slowed that down, that 3 for a couple of years and then factor of 2, and still by mid-decade you're able to see that. And I don't see any limitations on batteries because they're going to scale enough over that time frame. The only thing might have something to do with rare earths, but I really think they'll get that figured out, that there'll be enough of a supply chain by that point, because we're not demanding 1 billion tomorrow. There's still 10 years to kind of get that sorted out.
The only thing would be Elon did say he changed his number. He's now saying 1 million in 2030.
Yeah. So he's and again, these are like what the stretch goals would be. So that means, okay, rather than the 10, I think they can do 10 for a couple of years. Like I say, going from 27 to 28, 10 gets that's a big scale. Okay, from 100 to yeah, but they're making 3 million automobiles now a year, something like that. So they're 2 to 3 million is possible what they can do.
Yeah.
So and those are far more
out,
complex.
Yeah, CERN points out that a million humanoid robots is like equivalent to 50,000 cars, which is basically the first year of production.
Yeah.
It's not. It sounds big, million bots, but actually,
1 million bots is 30,000 Model Y battery packs. Yeah, that's a month's production. So there's enough batteries for that. So that's like 15% of the overall production, and that's ramping anyway. So right. You're not worried about the battery supply. The only thing might be the actuators are the hardest part, that they're the most expensive part.
Thank you so much, Scott. I mean, so that was very interesting. I appreciate the work you put in to cover this. We learned a lot. I mean, the design is so critical. And then now they're doing sim to real, and then you really parsed out what the statements have been of the AI team. That gave you a really good sense of what they were able to accomplish, what they're now able to accomplish, where they're headed. And it sounds like you're pretty optimistic in the sense that, they can now exponentially grow the simulation to real, like different any task eventually in the future. But you're still saying there might be some issues with the design that they still need to learn. And they made a hard choice here. And then you pointed out that with the choice they made in Gen 2, at this point, we don't think that it's going to be what they do for Gen 3. The only thing I'll say is that I think Tesla has the money and the time to be able to create 10,000 of Gen 2s and then completely redesign the bot for Gen, totally make the mistake of, they chose RAF instead of FAR. They change it later. Other companies, they don't have that. Mm-hmm. They make the wrong move. They ran out of money.
The safe move for the hip is FAR for now for a lot of companies.
Not what Tesla chose.
But and the thing is, when they change their hip design, there may be a new design on the market. Maybe something that's not FAR. It's completely, maybe there is some kind of ball and socket joint that everyone goes with.
Do you think so? Do you think eventually they will all go to ball and socket?
It's possible. See, the first thing you have to do is remember, they are designing this for sort of in-house use and also for their suppliers and other trade-offs, manufacturing companies. Mm-hmm. So that's the quickest way you get out there, the quickest way you scale. There's definitely, there are people that can pay $100,000 a year for these bots. So that's where you're going. They're going to be a little bit rough around the edges because they're in automation. They have to be robust and everything else, but they're not the design that's going to make it in the house. So again, when you start to get a couple million bots, at that point, you're entertaining the idea, these got to come home. So the bots that are coming home have to be a lot safer. These bots are not safe yet to be around people. There's a lot of changes. There's not even the safety standards in place to figure out what that is. So the idea of these being in the home next year, that's not going to happen. It's going to be a few years. And it's definitely not going to be this design. It's going to be a new design. Whether kinematically it's the same, that's possible. It's just that they're going to have to do something a little bit different in some places to make sure you don't have pinch points. It's not too heavy. So it's clearly going to be new versions that have to come in there. And they're going to learn enough to find out. But the design that they have seems to be adequate for the use case they have right now. And they'll be able to ride it for a couple of years. And then they'll come up with something new.
Wow, this was chock full of information. You only a few people like you really dig deep and really understand to explain it to us. The bot walking speed, that's something that we've been following closely. You've been doing that for a year, and now you've been able to confirm, not quite there yet, but maybe the new bot can now walk at 3 miles per hour. So we're begging Tesla to show us a video of it walking 3 miles per hour. And that's important because as soon as it can walk the speed of a human, theoretically, you can do the job of a human now at speed of a human. I mean,
especially, it can turn, it can pirouette. I'm pretty sure it can walk much faster now.
Yeah.
And with a full body control, then it should be able to walk also with a payload. at a
I'd love to
reasonable
see
clip.
a pick and place demo where it's actually walking as fast as human or moving everything, the whole thing as fast as human, because it is kind of like, that's what people watch. It goes, oh, that's cool. But then they'll say, yeah, but it'll pause, it'll turn, it'll walk slowly. Like, okay, but
we want it to be smooth, and I think it's possible, and it may be that they'll be able to show a few that maybe it's not like it's not fully autonomous, but they've been able to get enough moves in there to sort of demonstrate that the kinematics and everything can do it. So if they have something that, I don't care if it's not fully autonomous or however it's been trained, but can go over, get that battery tray like we've seen before, pick it up, walk it over, and drop it off somewhere else. And then we're able to see, oh yeah, it's moving quick, it's getting up there, it's getting up, coming over, dropping down. And when it walks with it confidently rather than like, oh, I'm afraid of dropping this thing. Now they get the full body control. They should be able to do that without stutter stepping along the way. And if we can see it doing it at a reasonable pace, it's like, well, that's pretty good because we know humans can go that fast. The thing is, by the end of the 8 hours, it's hard for a human to keep up. You're tired. You're tired. So there will be humans that will be faster, but then those humans will end up being like John Henry. They'll beat the machine, and then at the end of the day, they'll drop dead. So I mean that's how it'll be. Scott.
Yeah, I appreciate you researching not only Tesla, but you looked at 17 robots in total, and you compared exactly where they fall. No one does it like you do, Scott. Appreciate this. Thank you putting this presentation together for us. Very important for people who care about the future of human robots and investors in Tesla. Follow Scott. I mean, you saw the conversation he's having. Anybody who's anybody in robotics reaches out to him. Check out his. Actually, you should change that, right? You're no longer at Going Ballistic 5, are you?
No, it is Go Ballistic 5. Yeah, the handle's the same. It's just my nom de guerre is different. It's just the
so go to X at Going Ballistic 5, and then he's called Humanoid Bot Angelist. Love it.
Yeah, something like that. I can't even pronounce
Evangelist,
it.
Bot Angelist. Thank you, Scott. Thanks, everybody.
You're welcome, Herbert.
I've created a website that is the most comprehensive resource for the Tesla investor. Please check it out. Simply go to my website at herbertong.com.